So welcome back to part 2 of lecture 34. In the last part, we spent a lot of time looking at just a single operator, and we were trying to show that it's positive directly from the definition that we're given about the operator. And as we saw, it took a lot of work. You had to kind of break it up, and you had to do a substitution, and then from that substitution, you could deduce that it was always greater than or equal to 0. And you may not have all followed that. If you've taken Math 2 LA3, I imagine they would have done something similar to this. But if you haven't taken 1 BO3, I went through this very quickly. Now, the question is, like, there's a lot of work here to show that something is a positive operator. And in this part, I want to kind of give you a different way to check whether an operator is positive by using kind of the following characterization. Now, before I dive into that, I just want to introduce what it means for an operator to have a square root. So an operator has a square root if you can find another operator, such that when you compose it with itself, you get back the operator you begin with. Right? So this kind of agrees, the definition kind of makes sense, right? Because we say that 3 is the square root of 9 because 3 squared is 9. We just have to remember here, square means composing the operator with itself. Okay, so we have the following theorem that allows us to tell when an operator is positive. So an operator is positive if one of these conditions hold. And the second condition is kind of probably one of the more useful, is your operator is positive if it's self-adjoint and all the eigenvalues are non-negative. Okay, so rather than looking at that condition about being greater than or equal to 0, you could just look at the eigenvalues. Or you could look at the fact that t has a positive square root, okay? So that is, t can be written as r squared and r is positive. The other property you could look at is t has a self-adjoint square root. So you can find another matrix such that r squared is equal to t, and that matrix is symmetric. And finally, if you can find any operator such that r times r composed with its transpose is equal to t. Okay, now I'm not going to do the proof, right? We're getting near the end of the course. You've probably seen lots of proofs. So I'll just refer you to the text. And instead what I'll do is kind of give you some examples to show you the power of this theorem, right? So the previous example, we did a lot of work, right, to show that this operator was positive, right? And we were proving it directly from the definition. But what we can instead do is we could have used the second condition, that t is self-adjoint and all the eigenvalues are non-negative, right? So in this example, we would have that t is equal to 5 minus 2 minus 2, 5, right? So t is self-adjoint. Since MT is symmetric. And we also have that the eigenvalues of T are lambda equals 3 and 7, which is greater than or equal to 0, right? So by the theorem, T is positive, okay? So I want to point out, when we did all of this work here, we already saw that this was self-adjoint, and we applied the spectral theorem, right? So we knew that it's self-adjoint, so it's a symmetric matrix, so you can diagonalize the matrix, and when we diagonalize the matrix, we got this diagonalization, and these guys right here, the 3 and the 7, are the eigenvalues, and they're positive. So we could have actually stopped right here and said, hey, this operator is a positive operator. And I want to point out, just for those of you that have taken Math 2 LA3 and talked about positive semi-definite, what positive semi-definite means, and you may find this in the textbook, is saying that your matrix is symmetric and all of its eigenvalues are 0 or greater. Okay, so we're tying all of these pieces together. Okay, now the other interesting thing about this theorem, right, is saying that when you have a positive operator, it has a square root, right? So the theorem tells us we can find a symmetric matrix R such that R squared is equal to this matrix. And then the question you may ask yourself, well, how do I find that matrix R? And in fact, all the information you need is actually embedded in the decomposition that we already have, right? So using this orthonormal decomposition, what we do is we set R, we use the same matrix P, and then instead of using this matrix, we take the matrix where we take the square root of every entry on the diagonal and times by P inverse. And let me show you that this is the correct matrix. Okay. Then R squared is equal to P times root 3, 0, 0, root 7, P inverse P, root 3, 0, root 7, P inverse. These guys kill each other, right? P inverse times P, they cancel each other out. So we would have that this is equal to P root 3, 0, 0, root 7 times root 3, 0, root 7. And diagonal matrices are quite easy to multiply together. So you get P 3, 0, 7, 0, P inverse, which is your matrix A that you started with. Okay, so this is how you would find the square root corresponding to an operator. One thing before we take a break from this part is that you can actually prove that every positive operator, not only does it have a square root, it has a unique positive square root attached to it. So we'll stop there, and then in the next part we'll talk about isometries, which is peeking up right over here.